Thank you very much, everyone, for connecting today to the NfoLD seminar. NfoLD is the Network for Life Detection. It's one of several research coordination networks that the NASA astrobiology program is organizing to support research in astrobiology. It brings together enthusiasts of technologies and science around life detection. And we have a seminar every other month. So if you would like to present your work, please reach out to contact.nfold@gmail.com. We'd love to have these seminars more often, but it depends on your enthusiasm to present. Today, we're extremely lucky to have Dr. Pablo Sobron from the SETI Institute to discuss with us some of his work in life detection technologies. So with that, Pablo, thank you so much for joining us, and we look forward to your presentation. The floor is yours.
All right, thanks, Sanjoy, and yeah, thanks everybody who showed up in what seems to be a spring break week. I just learned, I guess. Right, so I think it's very timely. I think that we're doing this today after last week's LPSC, where more, as always, more science questions and answers get discussed. And what I wanted to show you today is a portfolio or a collection of new technologies that we've been building and we're building and will be building in near future to hopefully answer some of that astrobio questions and exploration in general. And so there's about 15 or so instruments that I'm gonna fly through. I understand this is being recorded, so you can always go back and check that. And my email is there. As always, feel free to contact me for questions. And one last item, I think last week at the steering committee here, we started discussing the possibility of having a database of instruments that are available and that are open to the network and others to utilize. So I handpicked, cherry-picked those instruments here that we can make available for not only for lab as a facility or service, but also as you guys think about proposals like PSTAR and things like that this year. A lot of these things are field ready. So with that, I'll just start. Yeah, so of course, all the work here is not me. Actually, it's in spite of me sometimes, but it's a huge team of people between the SETI Institute, other NASA centers, and Impossible Sensing here in St. Louis that made this all possible. So thanks everybody for the hard work. All right, so there is 4 main groups of instruments that I will talk about today. Anywhere from air to deep ocean. So let's start up high, air, and there's 2 categories here that we've been focusing on based on decadal survey work and, of course, the needs of NASA. And those are the atmospheres of planets and the plumes of some of the moons in the ocean worlds. One of my favorites, that's why I put it first here, call it Pulsar. And basically what this is, it's been funded by NASA SBIR, and this is a spectrometer that has no spectrometer in a sense. So what we're doing here is we're taking advantage of long fiber optic cables. We're using something that bothers people in telecom, which is that different colors travel at different speeds in a fiber. So we're using that to effectively separate the wavelengths of the spectra, Raman, LIBS, fluorescence, and others, without having to use optics in a box like any classic spectrometer that you've used in the lab or on Mars for that matter. So not only this removes the need for spectrometer, and for situations where there is a tether already, like something like a cloud platform on Titan or Venus. Doing this with a fiber has another advantage, and it's that we do simultaneous spectral, but also time resolve analysis. Again, if you look at the plot here, this is the kind of data that we're getting. This is a 1 kilometer fiber, but there's no limit as to how long the fiber can be, other than that the longer the fiber, the less photons you receive, right? There's some attenuation, but for 1 kilometer, and I think up to 5, which is probably the sweet spot, we can get good data. And what we're reading is time, basically, right? So we're counting the photons that arrive at different time, and we reconstruct a 1-to-1 spectrum. In this case, is Raman inflorescence of any sample that is placed on the far end of the fiber. So, and all we have to do is to have this optical assembly that we have here in the middle of the slide, which is the size of your cell phone, basically, and that's all you need, basically, to do this analysis, assuming you have a fiber, of course. But you know, on a balloon or aerostat configuration like here, this will allow you to deploy a low cost and low mass kites, I guess, for lack of a better word, here, and to probe at different depths in the cloud deck or atmosphere deck in different places as well, just by leveraging tethers that you might have anyway in the mission. So something a bit less exotic, although still pretty innovative, and also funded by SBIR and our own funding here. And this is a sampling system for atmospheres, which we think could be very useful for probes to Venus, again, or Titan, even Mars, and of course, plumes of Enceladus or Europa, where you have a fly-through situation where if you look at the lower left here, a picture of a drone flying through a plume, and this is a geothermal field in Iceland. So we flew the drone through with this cone collector, and this gray thing in the back here, that's a foam. It's a plasmonic foam, actually. So it's a foam that we built in the lab here, similar to aerogel, but we doped it with gold and silver nanoparticles, which are known to enhance Raman signal. And the result is what you see in the bottom, this yellow and blue spectra here, where, you know, in the absence of this plasmonic foam, with just a normal foam, the Raman spectrum looks like, you know, something that you've seen in the lab before, where you get frustrated because all you see is noise. So that's the case here too. But if you do a flyby now with this plasmonic foam, now you start getting all these very intense peaks here, which tell you a lot of things about the organic content of these plumes, and also the minerals. So here in particular, we're seeing some of the silica and some organics that come with the water vapor, with the plume that comes out of the vents. And some other tests that we did with rhodamine and other just testing different foams. But this is been tested in the field, and this is something that we've flown in the Atacama looking for dust, and also in Iceland, as I said before, looking for plumes here. So very direct application to some of the ocean world's plumes as well. This one I added here, and this is basically a remote lidar, classic lidar that you see in ISAT-2, for example, now the NASA satellite that is looking for ice sheet, sea ice, and canopy, as well as atmospheric effects in the cloud. But I put it here because what we've done is we've shrunk the volume of classic orbital lidars anywhere from the size of a small car to the size of a microwave oven. So it's a pretty significant reduction, because now, instead of needing to use a massive satellite, a $5 billion satellite, now you can start thinking about small sats, something that is like 100 kilograms, 200 kilograms, much cheaper to launch, and eventually CubeSats as well. And I think beyond Earth applications, of course, here, I think missions to small bodies and asteroids for recon, something like OREX did last year, where they used LiDAR to use that for EDL. Now we can use this LiDAR, which is a modified version of existing LiDARs, to do compositional analysis as well. So we can do mapping, pinpoint landing sites for sample collection, for example, for a small body mission. And this is basically a spin-off of a Matisse project that we have right now, of which I think you've heard about it today. I mean, in this group at NfoLD before, but the optics that we use is a spin-off that we put into this new concept here. So going closer to the ground, and this is where I'm gonna spend most time here, because of course, there's more rovers and landers than others. So this is a collection of the things that we think we want to do moving forward here. And the first one here is Merlin. So there is a video here of how it works. So I'm not going to spend much time here on that. But the idea is that in this black box, the enclosed thing, that's the magic box. And the window on top, we're shooting a laser through the window from the inside. So this is a back illuminated Raman system as well, with a peculiar feature here, which is that this window is not your typical sapphire window, but it's a plasmonic window. Again, it's a window that we have fabricated with nanoparticles as well that enhance Raman signal. In this case, we've seen enhancements of up to 10 to the 6, so 1 million times better sensitivity by using our plasmonic window, which finally enables to break the barrier of part per billion, the ppb barrier of Raman now on samples that you deliver to an instrument. So one concept of operation that we're thinking of for this is something like Europa lander type, or any rover or lander that ingests samples into the deck. And you think if you have cuvettes or sample holders that are transparent in the bottom, transparent meaning they carry our plasmonic window as the interface, then we can raster all of that from the inside of the lander or our box or volume, and scan the sample with the laser and getting this enhanced Raman signal into our detector. And the advantage of doing something like this, as opposed to your classic, like ExoMars Raman is doing, which is going to receive the sample on a sample holder, it's going to flatten it out, and you're going to look at it from a window like you would normally. What this allows you is to really separate your environments, so you can really keep the planetary protection chain very well under control. Because what you're using is you're looking at the window on the sample side from a confined space where we have our laser and all the optics. So this is funded by NASA Ames IRAD, and Mary Beth William is the PI here, and I'm sure you have talked to her or seen her Excalibur system, which is an extraction system to digest regolith and soil and extract lipids and fatty acids to look for these biosignatures on future missions. So this is the backend of that system where we receive these extracts and we can do the Raman analysis here. So we already done that, and what we've figured out is that on a Antarctica, some former Paleolake samples with very little organics, some of the less alive soils, if you want, on Earth, by extracting this with Mary Beth's instrument, and by then measuring the extract with Merlin, we have more than enough signal here, and this is CC and CH bonding, by the way, on the peaks that you see here. So we have more than enough signal to not only distinguish what organic pigments we have here. In this case, we have fatty acids, and we can actually quantify them again, because we have enough spectral resolution, but more importantly, enough signal by virtue of using our plasmonic window. So this is right now a benchtop instrument, but it's we're building the ruggedized version for field as well that can be taken to analog sites. Harpoon is another of our SBIR projects, and this one will be at TRL5 next year. And here, what we have come up with is with a very neat radical design of an optical probe. This is the box, if you want, that would go on an arm of a rover, and you shoot the laser from the rover or lander body through the arm, through the fiber. Play with the laser there, shoot on the sample, and get the light back, and shoot it back into the lander through another fiber. So part of the problem with that is, how do you keep the focal point always on the spot that you want to analyze, considering you are always going to have arm shaking and movement, especially in places like Mars where you have wind. So that is a big problem, right? So for long exposures where you need to really be in contact or very, 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 I guess, very precise spot. So we solve this problem here by doing real-time focusing of the laser and the collection optics, that's more important, on the fly. So we readjust the focus at the millisecond level without using any mechanical part. So this is very robust way to always guarantee in focus, Raman, ellipse, and fluorescence as well, spectra. And these are examples here of three standards that we have in lab, showing the optical performance of the probe itself. Even if you see a lot of complexity here in this breadboard, this is being built now into glassboard, which is using curved optics. So basically, we're making a little tube, if you want, like similar to the probes that you can buy commercially for Raman. Moving away from Raman a little bit, and let's go into LIBS. We have developed a super rugged, I would say, this is bulletproof, literally, system that performs in situ LIBS by using a handheld device. So a lot of you have probably used commercial LIBS systems that look like a gun, basically, and those are fine, but you would have find, like we have, that the performance of those are just not good enough to do science. They are good enough for process. If you're looking for one element in particular in your industrial application or pharmaceutical application, that's great. But if you're looking to explore and you're looking to really characterize terrain for whatever reason, could be just planetary exploration or ISRU on the moon or habitability, you need better performance. And we accomplished that by basically adding more optics, if you want, electronics, and came up with this handheld device, this form factor, which we think is amenable for eventually EVA activities from humans on the moon, hence the little demo here. And basically all the user do is you have a PDA or your cell phone, basically, and that's just what you're seeing. This little interface here, you get the data, and this is data, this is good. We'll analyze it later if you want, but move on to the next spot, right? So so this is the very first version that we delivered to a customer in South Korea. We are now designing the next version, which is about a third in volume and size. So getting comparable to the commercial offerings, but with dramatically better performance. And of course, not just for humans, but you can think about this as being put on a rover or lander as well. This is seems is a Biofinder of sorts. We had this funded by the Department of Energy for soil health analysis. The Biosciences Division of DOE, which does very similar work than NASA, turns out, when it comes to analyzing interaction between bacteria, microbes, and soil, and the chemistry and mineralogy. And so what we came up with is a real-time fluorescence hyperimager, basically. So now with a normal camera and normal lenses, we put in this little filter that you see here on the bottom right. That's our secret sauce. The filter allows us to basically decompose the signal coming back from the sample into particular molecules, or I guess analytes of interest here, to tell things like what you see on the left here: soil freshness, humidification, and health in general. This is the DOE application, of course, but obviously you can see how this applies to any other planetary application or surface where you're looking for organics that may be mixed there with your terrain, be it the ice of Europa or Enceladus on a lander, or some of the subsurface regolith on Mars, and even some of the organics that may be trapped in the polar ices on the moon. So this is a system that allows you to take basically a real-time video of the organics there. And the key here is the micron scale. aspect of this. So we can really zoom in very closely to look for these molecules of interest. And again, also handheld, as you can see here. This WIR, you probably heard about this or seen this for over a decade plus now, maybe. Wong here at Washington University in St. Louis, she built this over the years, and I was a postdoc here with her back in the day, and I took it to the Tier 6 mark where we are now. And so we made it as small as one humanly can do, less than half a kilogram, and fast enough to do real-time analysis. And because of that, we can start thinking about multiple deployment options. And what this is basically is you probably have seen already if you see the plot. It's a reflectance system. So we have active LEDs here, and you see in the picture on the right, a ring of LEDs and that are pulsing at a specific frequency, and they're shining on the sample, and the sample is giving you back the reflectance. Nothing new here, but here what we do is we really optimize the optics and the system to be very sensitive to small absorptions in organic content. And here the example is pretty extreme. This is oil, like motor oil, literally, and water, just to show that this is all these dips that you see here at 1300 and 1550, 1600, basically. That's the organic absorption. So we're working on we're using this as our regions where we determine organic content. And of course, the instrument goes all the way to 5 microns, like recent, but here we focus on this for this particular application. But so being so small, there is multiple ways that we could deploy this. Obviously, a drone or a flyer, if we demonstrate that we can actually fly on Mars, could be something interesting for this. Or on the moon, obviously not with helicopter, but with some kind of cold propulsion jets. But the point is that things like any lander rover, including clips to the moon, that are very mass starved, can fly this, and astronauts can use this as handheld device as well. This is the size of your palm, basically. And one application that we really like trying to push forward is that this is what you see in this plot here in the middle of the sketch. This is our configuration for a wheel mounted system. So think about a wheel, anywhere from MER wheel to MSL or Perseverance class wheels could mount this, and think about every time you do a revolution of the wheel, every time you go back and touch the ground, you get 1 data point. And that way you can use WIR as a ground truth system that actually tells you exactly where you're driving on, and can compare to orbital data. But also, as you are excavating, as you're drilling, as you're driving, you get information, first-hand information of the subsurface regolith as soon as it's exposed by the wheel. So you probably can capture some of the volatiles that you see there before they go away, or water included. So that's one of our more advanced systems. This is Tier 6, basically ready to plug into any mission concept. This is a Matisse-funded system that we will qualify for Mars applications next year. So it'll be a Tier 6. And here is another way in which we have broken the barrier of part per billion for Raman. In this case, we do it not by having any plasmonic system, but by rethinking the optical chain that goes into the spectrometer. And here we're replacing CCD with a single pixel detector, and we are adding a multivariate optical computer. We're basically doing chemometrics, if you want, on the physical domain in the physical world, as opposed to via software. So that's why we can really dig in deeper into what the compounds are made of, and how much of its particular molecule you have there. And here, the top middle plot, I guess the 4 plot there, showing colors and little bands on a rectangle. What you see here is how we discretize, how we really zero in into the molecules of interest here in the optical domain. So things that you've done before in the past, and you look at the plots here in the bottom, you get your normal Raman spectrum, and then you go into your library and you match the peaks to what you know should be there, or you think should be there, or you want to discover, and then you start applying PCA, PLS, all statistical analysis methods that can get you close to a quantitative analysis. But you require a lot of computational power and a lot of work to get there. So we remove all of that, and we are coding all that via hardware into the optical system, so that eventually the only data that needs to be returned by a mission is just what's the abundance of water in this mineral, or what's the amino acid content, or what is the level of this or such clay or carbonate in your sample. Reduces the data that you need to send back to Earth by a lot. So that's the innovation here, is this on-chip quantitative analysis of the compounds under analysis. And all it takes is, and I'm going down to the bottom right sketch here of the lander, is to just deploy a small cell phone size optical system on the ground, and then and that's it. So so you get the data. So pretty neat, we think, and also ready to fly starting next year. Okay, so now let's go a bit deeper, even see what we can do underground. And here we have a few categories of systems, and you'll see them in the next few slides. So going back to Pulsar, if you remember, this is the one where we replaced the spectrometer with a fiber optics. So of course, tethers and fiber optics are not new in space, and there is all kinds of concepts for applications on Europa lander systems that deploy cryobots or ice bots, if you want, that drill/melt through the ice and eventually reach the ocean and deploy underwater vehicles there. And most of those concepts call for a tether that transfer data and power from and to lander and cryobot. But it's also recognized that there is the ice on Europa suffers, it moves basically, so some tectonic effects there that will most likely break the tether. So we know that, and the system is ready for that, and there is a creative solution that we have to use actually the cleavage and the snapping of the fiber to our advantage to still be able to do things as we penetrate the ice into the ocean. But something easier than perhaps we'll see it in our lifetime is lava tubes or caves on the moon or Mars that are inaccessible by big rovers, but they are accessible by some other more mobile or creative micro rovers, if you want, like spider bots, things like that, that can crawl into tight spaces and rugged terrain and send data through a tether and a fiber down to the mothership. So this is another of the applications where we leverage an existing tether, and by adding no more than 1 millimeter of fiber cable to a tether and a few 100 grams, then suddenly we have a full science payload on this small boat that only has to carry about 200 grams worth of optics and electronics to do the analysis. So that's another application of this fiber optic spectrometer that we're finding. Another more advanced system here, and this is called DISCO, and this is also SBIR and will be at TL6 next year. And this one, sorry, jump again too fast. With DISCO, what we do is, if you think about March 2020 Perseverance, what we're going to do, as everybody knows here, but I will highlight it again in case somebody missed it. We're going to find the best place to core. We're going to get a core, 24 actually, at least, through the mission, and then we're going to bring the cores back to Earth. Now, the problem is that we are not going to know what the cores look like until they get back to Earth. we will know whether we have a core or not. There is a mechanism for that, but we don't know what the core looks like. We may be able to look at the borehole as we extract the core after, and look for textures and look for things there, which will be obviously symmetrical to the core, but we will not have first taste or direct access to what the core looks like until this is back here in the 30s, right? So we see that as a problem, and we propose this to build a system that cores, and this is a honeybee robotics drill system that is at Tier 6 plus at this point. And what it does is it brings the core out, but it provides a window through which we can scan the core as it's coming out. So as soon as the core gets extracted, the window will open and we will scan the core with imaging, Raman lips and fluorescence analysis all together to really get a picture of what the core looks like. And this is an example, a real example of a core that we got, and this is the maps that we are getting right now. And we're getting all this, which is pretty amazing already, with the breadboard that you see here on the right. And as we speak today, we are starting to build the central system here that you see on the left, with in the middle with the yellow lines here. That's what this breadboard, which is the size of a large shoebox right now, will become this year. It's the size of a couple of cell phones stuck together to be able to do the same thing. So we think that this adds very little risk and cost to a drill system that essentially can determine whether this core is great, it's an important core, it has good stuff that we can return back to Earth, or that we can keep processing in future missions where we may have, again, internal laboratories to analyze samples. So all of this is done by this instrument as the course is coming out. Now, other missions call for not coring, but for augering. So basically poking a hole like you do in your wall when you're going to hang something. So spring the drill bit, get the powder out, and make a hole, right? So that's what Periscope leverages that, and Periscope will go after an auger system, and we'll be getting hyperspectral images of the side of the wall of the borehole. And the advantage here compared to Sherlock and other fluorescence instruments that we're using today is that we are expanding our range all the way to 500 nanometers, so we can actually cover many more organic compounds, and much more importantly, we are adding again this time resolution capability to the system. That is what, in the end, is going to enable us to differentiate different compounds and quantify them as we're doing measurements. And this is a breadboard that we built under SBIR, and we will keep working on this over the next couple of years. And these types of images that we're getting right now with some Atacama salts provided by our colleague Alfonso Davila at Ames, and this is the type of things we're seeing. So all these images, what it means is that you have a temporal component and a spectral component that again point you towards what we have there and how much of it. And in the current configuration, Periscope is, let's call it Periscope because basically that's what it does, right? So you have light coming down the tube and then coming out of 90 degrees on the side. But of course, this is not rigid geometry. We can, bend this Periscope tube into whatever form factor to accommodate other architectures like surface scanning instead of borehole, or even remote UV imaging as well with Periscope. And so the secret sauce here again is the optical train and the spectrometer and the electronics that we are putting together that enable us to expand the range, but more importantly, add the time resolution feature here, which no other flight instrument has in this class of instruments. So we just, early this month, we got funded by NASA's new program, LUSTER, Lunar Science Technology Research, I believe, and also SBIR, and together with Washington University in St. Louis. Now we are working on a totally new concept for a new drill that not only drills, of course, but it also has a window on the tip through which we generate LIPS spectroscopy. We generate LIPS laser A, and then we collect the light all within a single optical line here. And this is the innovation here. Most of the LIPS probes or LIPS systems that you see, they have to double the optical path for a number of reasons, which would not make it possible to embed the probe in a drill bit. This is a 1-inch drill bit. This is basically the design of the Trident drill that is flying on the moon mission Viper in a couple of years. And what we're doing is we're basically poking a hole, and we have enough space now with our innovation in the optical train here to use a single optical path to both excite the laser but also collect light back. And ideally, this will be able to be plugged into a micro rover for lunar applications. That's the application for this particular program, since it's moon focused. But obviously, you can think about any other situation where on the ice of an asteroid or a small body or even an ocean world, you want to have a small lander or even a small rover crawling around and poking holes, down to 1 meter perhaps, or even longer, and doing LIPS as you drill. That's the important thing here. Is we're doing real-time chemical profiling as we're drilling down. And this is an example here of a LIPS spectrum taken on JSC1, the lunar simulant, and all the peaks belong to something, but obviously we're focusing here on oxygen and water. So this is the main focus of our research for this particular program. But this is, as you know, LIPS from ChemCam and now SuperCam. You know that it can measure all the elements in the periodic table. So we're not by no means constrained to water, but this is the application that we're funded for. And to finish here, let's go into the ocean a little bit. And there's two instruments that we're working on right now. So first one is the NASA PSTAR program that this summer, in August, September, will take us down into the deep sea at the Juan de Fuca plate. There is a hydrothermal field there at about 1.5 kilometers deep, about 200 miles off the coast of Oregon, and this is an NSF facility that has a cable. So we're gonna be flying, or diving, I guess, our invader payload in this tower that you see on the bottom left here. So you see, this is a 4.5 meters tall tower. It's a lander to all effects. And the blue parts here, this is foam that is gonna help us keep buoyancy on the system, so that an ROV can use the handles that you see here to position it at the right spot, and also adjust the feet that you see here on the bottom by turning, adjust the level to make sure we're stable for our mission. And we need to be stable because we want to be working there for a year. So this is a year-long mission that will return daily maps of a chimney like the one you see here in the top part of the slide, that contain not only organic matter, and in this case biomats here, but also, of course, chimney and vent materials, plume coming up with hot fluids and nutrients, but also all the minerals that precipitate and make the plume what it is. So make the chimney what it is. So we're deploying basically the payload is only the top part of this tower that you see here, the cylinder on the top, that has a gimbal system that be able to scan up and down, left and right, to get the full picture of the vent. And we also have stereo imaging, and this middle messy plot that you see here is just the first attempt that we've made at reconstructing the 3D structure of a chimney by using stereo imaging alone. So we're getting resolution in the micron level, or at least 100 microns level of features in the chimney in 3D, just by using stereo imaging with some laser line scanning tools as well, but essentially it's imaging-based system. And that's one part of the equation. The other part is that this laser sensor that you see here on the test on the tank, it's shooting a green laser, also UV laser, but you don't see it, into a rock. We're going to be positioning this system between 2 and 4 meters from a chimney. And at that distance, we're going to be able to do for the very first time a long-term resident system that is doing high-frequency measurements of the geochemistry, the mineralogy, and the organic communities that exist there in the vent. And of course, you see, I guess the reason why NASA is pushing for this is no other than knowing that there must be vents of this type in black smokers in particular, or even alkaline vents, but vents nonetheless on Enceladus and Europa. Testing these technologies on Earth first, it's required to eventually go to space. But turns out that we really don't know much about these vents anyway on our own planet. So what NASA is doing now is not only providing path to flight for these technologies, but providing new science to the ocean community on Earth here. And last but not least, here in this picture, you see the system on the bottom here. This is a drill that Honeybee Robotics built, and this drill will be deployed in parallel to the lander that you see here by a different vehicle, by an ROV. And this drill will allow us to get six core samples from the chimney that we can bring back to Earth. This is our return samples to really do a very in-depth study of the cores, and then to benchmark ground truth, if you want, the data that we'll be collecting over the year with our Invader payload. So it's an end-to-end mission, if you want, that in a way simulates what 2020 is doing by sending a rover lander in our case, and eventually bringing samples back to Earth. Luckily, we don't have to wait till 2030, and we'll have the samples here this year, so we can actually do some science right off the bat. So this is Invader, and given the potential impact and the successful tests that we have so far, we got into contract now with another agency called BOEM. This is the Bureau of Ocean and Energy Management. Depends on the Department of Interior, and also with support from NOAA and the USGS. We are now building the next generation payload that is going to be small enough now. It's going to be like a shoebox, if you want, of size. And now we can finally plug this type of payload into ROVs or AUVs, eventually, flyers that will scout and map out the seafloor for the purposes of this agency's missions. And BOEM is interested in knowing critical minerals and critical elements. You all know that it takes a lot of rare earths and critical elements and minerals to build batteries for your EV cars, and also for the wind turbines. And as we keep going the green tech way, we'll need to get more and more of those minerals. And so happens that China has all of them, and the US has none of them, or very little of them, on the continent. But we do have a lot of them in the continental shelf. So BOEM's mission is to find out and map out the shelf, and the other shelf actually too, to find these minerals. And this is what we're delivering. It's a system that does what you see on the bottom right here. In this case, we're focusing on audio, but regardless of the particular use case, what we do is, again, stereo imaging, and we do a raster scan with our laser to eventually map out the abundance of and distribution of minerals in particular areas. And this is small scale, and audio is the size of your fist. But obviously, you can scale this up to kilometers if you want, and be a bit more, a bit faster, right? So you don't need to do a 100 microns scan of every rock in the ocean. You can scale it up to kilometer scales as well. And again, the types of data that we get are maps of abundance of minerals everywhere. And of course, NOAA and USGS want different things. They want to have a catalog of the habitats that exist there, with potential benthing communities as well. So this instrument, because it has fluorescence mode as well, and based on the things that by now you've learned that we can do our time resolved, we can quantify and distinguish all the organics that we want, we'll be able to deliver that as well. That's why they are on board on this project as well here. And I think, I believe this is the last slide. Yeah, so I will stop here. And I think we have maybe time for a few questions. And otherwise, you have my email, and I think Sanjo and team will make this available for asynchronous view, I believe. So yeah, feel free to contact me anytime today if your question doesn't get in the queue. Thanks, everyone.
Thank you so much, Pablo, for this incredible survey of the instruments you're building. Very impressive diversity of tools for diversity of science. Really, really impressive work. The floor is open for questions. If any of you have something to ask Pablo. I'll start with one then. Pablo, I didn't quite get how your spectrometer-less spectrometer works. Yeah, so if you ask anybody in AT&T and everybody who does telecommunications with fiber, so you know that because you're using glass essentially to guide your photons, the refraction index is different for different wavelengths. So you find that I may say this wrong, but it's either or. Either the blue photons or the UV photons go faster than the red and infrared, or the other way. But anyway, the point is that some photons go faster than others. So on a long enough fiber, what you can do is you can measure the time of arrival of your photons. And because you know the physics and how fast they travel, you know exactly at what time you're clocking in what colors, what frequencies. That's the key. So this is a big problem for telecom, and actually it's well known, but we thought that we could make the problem into an advantage, right? And I think we showed that it works. So yeah.
Hi, Pablo, great talk. That was really, that's a lot of information and very cool, and a lot of innovation and a lot to take in. For the IC project, the kind of like ramen that seems to compress spectra or send it back without spectra, I could see that being a problem with sending back spectra from another planet of fatty acids without having the actual spectra. So do you all have like a way to kind of like check what's going on for false positives, to be able to actually show the spectra if you do find something interesting?
Yeah, so yeah, it's a great question. So I skipped all of that, but what the system does is the first spectrum is a swipe. So we go through the whole spectrum and we get the classic spectrum. And then we have a machine learning tools that we developed here to really understand where the peaks are and which ones are important, and then focus on that and do the quantitative more in-depth analysis of that. So the choice is up to the ground loop, right? And on Mars, Moon, there's probably no problems in sending all this data back. On Europa or Enceladus, you may have trouble with the engineers telling you that too much, right? So that's why we're building that capability to be ready for minimizing, distilling the information that you want. But you're totally right that the core and the key problem here is to make sure the machine is doing what the scientist wants it to do, right? Without making too many mistakes. But yeah.
Awesome, thank you.
I have more of
Pablo,
a curiosity.
how do you deal with scattering of light? Oh, go ahead, Brooke, sorry.
I had more of a curiosity question. I was wondering, do you have people that are doing field work that, these instruments weren't necessarily designed for originally, that are like hiring? Like when you talked about providing this to NfoLD as far as like an accessible database when we were talking about putting these instruments up, like, do you foresee if I'm headed out to the field in Antarctica, deploying some of these things? Is that how you're operating?
Yeah, that's exactly the way we do it. So,
okay.
So we're part of a number of PSTARs, and we actually lead one, and we'll. Unfortunately, I've been itching to go to the field for the last year plus, but one thing that we did in the SETI Institute, and we had this NAI project to go to the Andes twice a year, basically for the last 4 years. And Natalie Cabral was the PI, and so that's exactly what we did. And that's why some of these technologies have been matured, is through field work. So yeah, so most of them, are ready to just be taken in a plane and go to the field whenever we can.
Okay, cool.
Pablo, how do you handle the scattering of light with the laser underwater? It seems like all the particles in the ocean would cause havoc to your laser signal.
Yes and no. So you're correct that the glowing green thing that you saw in the fish tank, that's exactly what happens because of the reasons that you mentioned. But think that all of that is a beam that is not focused. The beam in the end will focus on the sample and only on the sample. So most of the photons will be delivered to the rock, to the vent in this case. So I'm gonna give you a number here, but maybe 90% of the photons that we get are from the sample only. The other 10% is from the scattering from the ocean and the light and whatever is suspended in particles there. So it is a problem that we need to mitigate, but it's not a deal breaker at all, given the tests that we've done before, that we know how to take care of that.
Thank you. There's a question in the chat by Stephanie Cullen, and she asks, what is the breadth of machine learning being used in the post-processing of time-resolved data?
So for now, we're just doing database population. So we are building the database, we're building the learning tools before we start training them in the machine. I'm happy to discuss our ML AI approaches offline, maybe, or different talk. That's a whole different hour of work that we should be talking about. So yeah, Stephanie, if you have any questions, please feel free to just shoot me an email and we can maybe talk offline.
Any other questions for Pablo?
I have other random, I don't know, somewhat specific, more thought questions. So I think it was slide 2 or 3 where you show that you've got this funnel. I'm looking at some of my notes, right? And I think when you collect those particles, does it go? Did you say it goes into a gel?
Yep.
Right, and then you do your Raman spectroscopy, correct?
Yep.
Have you ever thought about designing the gel to where it's like a digestion agent, or it does some other incubation with the material or the particles you've collected?
No, and I'm intrigued about this. No. Maybe we should thread some notes later on this. So
for everybody that's on the call, I think there's a variety of us doing different types of chemistry. I'm a protein chemist, so a whole particle does me no good. I need it to be broken down, but I'm sure there's other people doing different types of chemistry that, I don't know, it just seems like I didn't realize that when everybody did these kind of plume collections, you collected everything into a gel that you could put whatever you want into it, right?
Well, cool. Yes and no. To qualify gel to fly, right? You need to make sure you can clean it and you can, certify that it's not contaminated. And so if you look at so we use Stardust Heritage, the mission that collected materials coming from a comet. And it was shown, well, a successful collection can be done, and it brought samples back. But the problem is that a lot of the organic analysis were deemed eventually contamination from Earth, because think about these gels are essentially empty. They're 95% void, right? So how the hell do you clean that, right? And I think our gel has not been flown again after that. And I suspect that's part of the reason. So what we're trying to figure out is what kind of inorganic I guess structures or gel, maybe even metallic foams we can create that remove the problem of cleaning. But I think we're not at the point yet that we need to start thinking about that, which means that it's a good time to think about this other application that you mentioned, because it's still early on in the game where we can adapt to more scientific projects. So I will send you an email on that later this week. So this week, actually, NASA announces the SBIR phase 1 selections again, probably in a couple of days. So we proposed a couple of things on those lines. So maybe what we'll do is, based on what we win or not, if we win any, I will shoot you an email, and maybe we can redirect the science towards something that is useful. Yeah.
Well, thank you very much, Pablo, for a very stimulating seminar and for taking our questions. I learned a lot about the diversity of things you can do with a Raman and where you can put them. It's been really, really, really fun. So this is the webinar of NfoLD. It happens every 2 months. If you're interested in presenting your presentation, please let us know at contact.nfold@gmail.com and we'll put you on the schedule. Pablo, I know you're obviously very busy. Thank you so much for chatting with us today. This is very insightful.
Oh no, thanks for having me, and I'm very happy to see a lot of familiar faces here. So hopefully we can have this meeting in 3D at some point soon.
Yeah.
All right. Thanks everybody.
Look forward to that.
Thanks, Andrew.
Thanks, Pablo.